Hi everyone. Good evening, good afternoon from wherever you're joining us from. Thank you so much for joining us today, and I hope you guys are doing great. And let's just get started. Apologies, we are starting 5 minutes late. Today, my name is Moluwashe Yayedele. I'm a co-organizer for GDG Ajah. I'm also a mobile and POS engineer. And so about GDG Ajah, GDG Ajah is a community of tech enthusiasts, developers, and designers around the Lekki Ajah in Lagos. So we leverage on Google technologies, and we host tech events that can help our communities. We host workshops too that can help our communities. So I know you guys might probably have heard about DevFest before. Something that we host often too every year. And so we also have an event coming up too, soon, which is the Google I/O Extended. So we've hosted a lot of events, over 30 events, and we keep hosting. So today we are kickstarting the data structure and algorithm class, and so we hope you guys are going to make use of this opportunity to start learning data structure and algorithm. For those that have started, we hope you guys are going to use this to refine your knowledge about DSA. So thank you so much once again for joining us today. And so I will be sharing the community link. We have community on Bevi platform where you can join us if you have not been part of the family. And also we also have a WhatsApp community, and we also have the Slack community. So I'll be sharing those links in the chat box soon, so you guys can join us for those that are not on our community yet. So on today, very sure you guys have seen the curriculum that we've shared to your email, and based on what we are going to be doing based on what we are going to be doing this throughout this book. And today we are focusing on intro to DSA. And so from June 17th to July 15th, we are going to be focusing on data structures. And from July 22nd to August 19th, we're going to be focusing on algorithms. So on the 26th of August, which is the last day of our bootcamp, we are going to have a soft skill session and a competition. There are a lot of prizes to be won. We are going to communicate that to you guys later. Moving on. So for each class that we are going to have, there is a structure which our awesome tutors have. We are going to be following, and for this, for you guys to get a very good knowledge of what you guys are going to be learning throughout this bootcamp. So the first is going to be, there will be a lecture on the topic, and the particular topic that we are going to be treating that week. Also, there will be patterns associated with that topic with examples that we share with you. Also, there will be some take-home assignments that we share with you. So we expect you guys to try your hands-on experience, like on code, like try thing based on what we've learned throughout that class. We expect you guys to try something and submit the assignments to us. So we are going to share the GitHub repo where you push your assignment to basically. So there will also be additional study recommendations from our awesome tutors, which we will share with you for after every class. So, and I want you guys to remember to check your email for updates every time. It's really important. Also, submit your weekly assignments, fill the weekly feedback form, because these are the things that we use to improve the bootcamp, to improve the classes and all. So, and also join the DSA Slack channel. We've sent an invite to everyone. So try as much as possible to join the data structure and algorithm Slack channel, so you can ask questions, and you can get other people. You can sync with other learners too at the same time. So please try and share this on your socials. Let us know about your journey using the hashtag GDG Ajah, GDG Ajah DSA, GDG Ajah Bootcamp. So not to waste so much time, we can't wait to witness your growth and achievement during this bootcamp. So we'll be moving forward to start why we are here today. So today we are starting with intro to DSA, and we are going to, and also time and space complexity, the big O notation, which is going to be handled by our awesome speaker tutors, and Oluwase Ibelo, who is a software engineer at Google, and also Soji Egbonwo, the team lead senior software developer at Velo, Canada. So I'll be handing over to them now, and so we can get started today. So thank you so much, everyone, and see you guys later.
Okay. Hi, everyone. Okay. Do I have access to share my screen? Okay, I think I do. So it's so great to be here. I'm sure we're going to be having a swell time in the next 3 months, right? I think, yeah, it's about 3 months. Okay, so Sheye has already given introduction into what you should expect. Right, so let me share my screen. Come on.
Your mic is muted.
Please, let's just give
Okay,
him
yeah, I think it's okay.
yeah.
Now,
All
it's
right.
okay. Yeah. Okay, so I'm sharing my screen now. Sorry for that disruption. Can you see my screen? Just a just an acknowledgement. All right, I think
Yes,
I
we
can.
can.
All right. So I'm sure it's going to be an interesting journey on DSA in the next few weeks. Okay. So we'll just start today with the introduction into the topic, and from here, we'll begin to go into uh, the full, at least the rabbit hole. So today will be easier, introductory, just to focus on uh, the high level descriptions and definitions of certain terms and the kind of things that we should expect. As Sheyi mentioned, the first stage will be in the first few weeks will be focused on the data structure, and then the last weeks we focus on the algorithm aspect of it. But and then eventually everything ends in a competition. But today we are just going to be looking at this, what you're seeing on my screen right now. I choose to start from the benefits rather than just, go through data structure, algorithm, benefits, and then looking ahead. Okay, I somehow think it helps us to like set the expectations right at the beginning. So to start with, where am I? Omoba. Okay. All right. So this is just where I think I am. I'm a technology person, a programmer with experience in multiple languages and experience across various industries. Worked with certain organizations you are very familiar with in Lagos, there, including Swift Network, Cyberspace, Jam, Charms. Okay, so currently I lead a team here in Canada. All right, that's not why we are here. This is why we are here. Okay, so we're talking about data structure and algorithm today. And as an introduction to the topic, I would like everyone to uh, understand data structure and algorithm as a very key aspect of the world or the discipline of computing. Okay. You are not told this when you started programming. However, the mode of entry you had in coming into this programming, whether it was planned, unplanned, motivated, you went to school to read computer science, or you are currently reading computer science or any engineering course, probably you did not see something like DSA coming. All right, you didn't see it, wasn't there. If you start up, if you go into any language, Kotlin, Java, C Sharp, and you express interest in the language, the hello world you come across says nothing about data structure. Okay, and when you run the hello world program, you just see an output maybe on your console or on the GUI. It looks fantastic. It looks interesting. Okay, you are happy with the output you get. Okay, that, oh yeah, you started programming, then you start learning the language, the syntax, the structure of the language, the keywords. Then you go into libraries that you could use to get certain things done, like printing, connecting to database, or achieving other functions that are already encapsulated in the language. Then you use frameworks to help you build applications. So you could be in this programming field for 2 years, 3 years.
I saw you. Sorry, please, we can't hear you. It's muted. Sorry. Oh, you're muted.
Okay, yeah, I think it's okay now.
Yeah.
I think somehow I was muted. I don't know. Okay, so you could be in programming for some time without coming across data structure and algorithm until you encountered a problem.
I saw you. Sorry, I think you are muted again. I saw you. Can you hear us? I think you are muted again. Sorry.
I think it's okay now. I can enable it now. Okay, I think what happens is once I put it on slideshow, it muted my mic. So I won't put this slide on slideshow anymore. Okay. All right.
You can
Sorry.
slideshow. Sorry, you can put it on slideshow. I think it's an admin issue.
Okay. All right. Let's try it again. Okay. Can you still hear me? All right.
Yes,
I think it's okay. All right. So I was saying that you could be in programming for some time without thinking about data structure until you hit some brick wall in functionality or user experience, performance, and all. Or you have big vision of joining certain technology companies, and when you attend an interview, or okay. So, but whatever your means of encountering this topic, data structure is a key aspect of computing. All right. Generally, the physical aspect of the engineering, the logical aspect of the network design, information processing, the artificial intelligence, or the logical processing aspect of computing, these are not complete until data structure, the topic we are talking about today, DSA, data structure and algorithm, like completes the whole block. Okay, so it's a key aspect, foundational, okay, and which is why it is taught in school. Okay, but even back then in school, in your computer science classes, you probably did not put it in the right context, like understanding the essence of this, at least with respect to performance, quality of the application you build. Okay, you see data type of integer, float, or boolean, string, okay, without thinking so much about how they actually work, how they actually impact the kind of applications you build or the kind of experience you want to give your users. Okay, so this topic is first important on the theoretical aspect of it because computing, software programming, okay, is based on artificial language. I just need to set this straight. I wish I could emphasize this more. Okay, what we are dealing with today, computing as we have it today, is not natural. Okay, built, okay, because it's not natural and it's built, there are sets, it works based on certain abstract principles. Okay, so we need to understand those principles. Okay, the principles are like what we have, how the systems have been designed, okay, to work cohesively, like work together. Oh, okay, so you need to understand how data works in programming, in computing, and then how if applications, the higher level events like applications or different kinds of applications, databases, or whatever aspect, whatever kind of enterprise system or social networking system, whatever system you're building, they are actually based on those fundamental principles. So larger content concepts, modern application, think of any application right now. Is it your Google map? Is it your social media sites? Okay, all of them are based on these fundamental principles, which I've said. They are abstract, okay, they are logical, okay, and they are, of course, made up by us. Okay, so and we need to understand them. We need to pay attention to them more than we have ever done. Okay, and get this right, please. The reason why I want to emphasize this, you should take this important, is not so much that you get or you prepare for an interview. Okay, I will speak more on that later. It's not so much for your interview preparation as it is for what you are currently doing. What are you doing currently? All right. Okay, that's where we're going to the practical aspect. What are you doing currently? Probably you are learning software development. You are working in a company right now. You are a student. Okay, whatever your current status, all right, understand that DSA is needed for you to build an application with enhanced runtime, okay, where your application performs at least to certain expectations, okay, you are able to build a highly performant application that runs fast, uses less space and memory. Okay, even if memory seems to be cheap now, a typical system comes with maybe 16 gig of RAM and 1 terabyte of ROM of hard disk space. Okay, your application runs within a context. Okay, and you have to be concerned about how it runs, how long it takes to run, and how it behaves when given certain types of data or certain amount of data. Okay, so my co-facilitator will be talking more later on that aspect of runtime, time and space and complexity. Okay, so understand that wherever you are right now, don't think about the next job. Don't think about what you are looking forward to. Put it in context that you need to understand this. You need to apply this where you are. Okay, and you will see how that it helps you. Okay, so this is applicable to all of us, whatever your area of software development, whatever platform, iOS, Android, are you at the front end, at the back end, in the middle? Are you a database designer or developer? Okay, you actually need this concept. Okay, so even if it applies to all may not grasp it, all right? But if you want to distinguish yourself, if you want to, like, okay, be attractive to high-paying companies or companies who are really doing the next, who are pushing the next frontiers of technology, all right, you need to pay attention to this. Okay, so this is a very important topic. And on talking about the values, okay, the benefits of it. No, okay, so the benefits, as I mentioned, is far-reaching. Far-reaching in the sense that it applies to whatever kind of application you are building. Don't only look at it like, okay, I'm a front-end developer building the UI. No, it applies to you. Okay, and you'll see later in this journey how your variable declaration already sets you up either for failure or success. Okay, so you have to get to that point where before you declare a variable, you actually think about space. Then you think about operation that will run on that data and how long it will take. Before you use an iteration or a loop statement, you want to consider the beginning of the data and the end of the data, how long it will take. Okay, so to know how to prepare for that. And because it applies to everyone, you begin to see that it builds your problem-solving skill. You are able to solve performance problems. Okay, and of course that contributes to the quality of your application or of your work also. Okay, because the earlier decision you made about variable declaration, data input, the use of iteration or the use of recursion, whatever, you have made a deliberate choice. Okay, considering what kind of operation will run on that statement, in that statement, what amount of time it will take. All right, so it helps in your application quality. And of course, this will make you productive as a person and then build your confidence. Okay, I will speak later on looking ahead, what you need to begin to do to build your confidence. But please know that the benefit of this includes what we have mentioned here. It is not just to get the next job. All right, I will emphasize that again. Whatever status, wherever you are currently, please, you need this to remain top notch as a developer. You need this to be productive. You need this to solve problems. And over time, you see much more benefits than this. Okay, so that said, quickly, we will just look at data structure at a high level. And as we go ahead, I must say at this point that if you have any question, you can type in your question in the message board. The moderator will look at them and then prompt me, okay, in case there's any question. Okay. So looking at the left leg of the topic, data structure and algorithm. Okay, so that is on the left. Remember how when you are in school, your lecturer or your teacher comes up with a topic and then tells you that many people have given different kinds of definitions. All right, this one describes it this way, that one describes this way. Then the story ends with saying, okay, this is the definition we'll go with. All right. Unlike that, yes, we won't go with any particular definition here. All right. We will just project how various people, experts, articles online have described data structure. No, okay. They are saying the same thing in different ways. Oh, okay. So the simplistic aspect of which you find that, yes, data, we have an intuition what data is. Yeah, we say data is information, right? Okay, that's okay. At some point, we look at it that, yeah, discrete values, okay, that convey information. Yes, because they are discrete in the fact that they have specific limit, size, and belong to a particular type. Okay, they could be seen as quantities, characters, symbols, okay, on which certain actions or operations are performed. Okay, specialized format, it begins to get much more interesting when some people say it is specialized format for organizing, processing, retrieving, and then storing data. So it is getting wider at that point. Okay, so at this point, looks like we are moving away from just the data to how it is structured. Okay, specialized format. Okay, and Robert Sedgwick is a renowned expert in this field, has written a book on the topic of algorithm. Okay, and then his own definition is, yeah, schemes. Okay, conveying a sense of structure, schemes for organizing data that leave them amenable to efficient processing. All right, I wish you could have given probably a simpler description, but what Robert and Target said are similar in the sense that, yeah, data structure is more of how your information is structured, okay, ahead of their processing, or how that your data is structured according to the kind of operation or application you are going to build. I'll say that again. So your data is structured or organized according to the type of application you are going to build. No, okay, and you see that the whole journey is about how different data and their structure are amenable to certain processing or are fit for certain kind of applications. Okay, so know that at a general level, it is not just information, it is how it is structured. It is how it is organized. And there are different structures, okay, for different kinds of applications. Is that a question? All right. Yeah, so key points about data structure. Okay, so as you begin to think about data structure, think about input. What will be given to your application? All right. What will be typed in? Be whatever the input is belongs to different type. You know, you are familiar with certain data types, primitive or complex types. The primitive types like float, integer, double, long, string, okay. So, and then before you move to the complex type of data that are object in shape, okay. So you are thinking about what size your kind of data has, the maximum or the minimum and the maximum bound of your data. Okay, what the amount of memory or the amount of space it takes. Okay, all right. So you are talking about the input, the type, the size, memory. Okay, then this is important. One thing you will begin to do in the next 3 months is begin to visualize data. Begin to visualize structure. I will come back to that later. I'll come back to that. What I mean by visualize is very, very important. Remember, I said earlier that this topic is theoretical. Computing is theoretical. It's artificial, rather. All right, it is artificial. See, it is abstract. To help you, you need to have a mental model, okay, of whatever data type we are talking about. So you'll see how that comes in later. So another last point I'll mention on data structure is that how your data is structured eventually determines how it's going to be saved, all right, or persisted. Let's use the word persisted. That is why later on, of course, in our current world, you have different database management systems based on different database persistence philosophy. So you have relational database, you have graph database, you have document type database. Okay, of course, those database applications have nothing to do with data structure algorithm. But what the linkage here is that those database structure, relational database, document database, key value database, graph database, they have data structure in mind. All right. They are applications, just like Google Map is an application, but they have come up with this application based on how their data is structured. Okay, it may look a bit complex now, but let's go ahead. In the next 3 weeks, you will begin to understand. Now, just a quick way to like make sense of data structure. I don't know if this will help, but something I feel like projecting. Okay, we all know that the way computer stores our code or whatever we're doing, your movies, your files, your application, to the computer at the lowest level, they are just binary digits. Okay, they are in ones and zeros. Okay, in the computer or the machine language itself, ones and zeros. Okay, on top of that, before then, we have encoded character, okay, which is fed whatever kind of application, whatever input into the system is some form of characters, some form of input encoded, whatever the encoding type that is used, okay, become transformed into ones and zeros. Okay, the encoded characters form a data, okay, a set of data. So a simple way to look at it is look at data itself, DATA, D being is stored in a particular encoding. So an arrangement or a set of characters form your data. Whatever the data is, it can be movie or whatever. A set of characters make up that data. Then that data is organized, formatted, structured in a kind of way. Okay, so at some point you are thinking about certain concepts like node, array, list, stack, queue, tree, graph, hash, node, a kind of structure. And the structure, or based on this, how you've organized this data, your data is amenable. That is, it is open or much more efficient for certain operations. Okay, this is high level. I don't know if this makes sense to everybody. I just project this to like give you a sense of how at the fundamental level, ones and zero are rolled up into a bunch of characters. They make up data. The data is structured in a particular way, say maybe in a graph. And then because you structure your data as a graph, then you can build a Google map out of it. All right. But because your data is structured as a stack, all right, you can build certain operation out of it. Okay. So we can discuss this further later on. Okay. So last on the data structure is to look at another way to visualize this is simple enough. Like if you talk about data structure on the primitive side and on the complex type of it, the kind of things you will see under them. I won't spend much time here. I will discuss more of these forms, major part of our discussions along the journey. Okay, key takeaway from this on the data structure, please be familiar with your common data types, the generic data types in computing. Okay, they are pretty much the same or constant across languages. Okay, your float, your list, your string, and all. And then be familiar with with the data types and how they are represented in your chosen language, your favorite language. Okay, so if you're in JavaScript, know how data is structured, how it is handled, okay, in that language. Okay, don't look elsewhere. Pay attention to your own language or to the set of languages you are using, how their data is organized, how they are structured. Very, very important. It will determine the kind of applications or the kind of processing you can run. And much more than the primitive type, you'll find that in some languages, you have linked lists, you have matrix. Okay, so if you have matrix, probably you don't need to build your own matrix. You can easily just like instantiate those data type and begin to use them. Okay, so be familiar with, check maybe the first 2-3 chapters of your language. If you take a reference book or a book in C# or in Java, the first 2-3 chapters will be on data types, where you'll be introduced to the generic and the specific types of that language. Okay, moving on to this, we'll wrap up. I should be done in the next 10 minutes max. Okay, so algorithm at the right side of the equation, okay, focuses on operations, okay, operations on the data. Okay, so again, can be described in different ways, all right? We have a sense of what it is in terms of, okay, yeah, some will say there are rules, okay, there are rules and instructions that turn data into something useful to program it. Some will say a set of finite rules or instructions follow the calculations or other problem solving operations. Okay, Robert Sedgwick, methods for solving problems that are suited for computer implementation. Okay, so methods for solving problems that are suited based on your data structure. So some people have said that program is data structure plus algorithm. Okay, data structure plus algorithm gives you a program. Okay, so key points to know about algorithm. Okay, there are rules. Okay, rules is in terms of description of how a specific task is done or is implemented. Okay, that it describes what to be done to arrive at a solution. Okay, it is bounded being that it assumes a particular set of data will be given to it. So it works based on a data type or data structure. So that is why I put a structure dependent. So if you have an algorithm for a list data structure and you put in a graph data structure, then that algorithm will struggle. Either it fails, it falls, or it performs abysmally slow. Okay, so your algorithm assumes that you are giving it a type of data structure. Okay, so they are the operations. The focus of algorithm is on the output. So why the data structure focuses on input and how the input is structured, the algorithm focuses on what comes out from it. What comes out of your Google map is direction. Okay. All right. So it focuses on time and space complexity. I won't speak much on that. Okay. So specific attributes of algorithm. Okay. We'll see this as we proceed in the journey. How that various algorithms are targeted towards specific purposes. Okay. So there are different purposes. There are multiple algorithms even for certain problem, for the same problem. But as we see later on that the chosen algorithm has impact on performance. And there's one that performs faster than another. So you see it as we move along. Okay. We'll talk, I won't focus much on this because these are what we'll be focusing on later along the journey. Standard techniques of algorithm, like greedy algorithm, divide and conquer. Dynamic, we'll talk on dynamic, maybe not so much, but you get to see some of these techniques and we'll probably come up with a problem and then solve that problem with these three types of algorithms. So you can see which one performs better and why probably you want to focus on one and not the other. Okay. I will leave this to my colleague to focus on time and space complexity. Okay. Making sense of the algorithm. I've mentioned it, but I need to emphasize this. Put a link here that you can use as a reference to understand common operations applicable to various data structure. I think I have it open here. So real life applications of data structure and algorithm. You see it in this link. Is tells you, talk about stack, queue, tree, what kind of applications are there that you can build with it. So something for you to reference after this topic, just to see what you should expect. Okay, this is my last slide. Okay, looking ahead to this topic, I want to start somewhere. This topic, because it is not natural, it is artificial. I will advise everyone to calm down. Okay, please calm down, be patient. Don't rush it. Be patient with yourself. Okay, all right. You may not get it in 3 months. Okay, you have not failed. You just need to begin to read and practice and practice and practice and read again. And just keep going through it. Staying there helps you understand it. Okay, the more you stay there. It's good that you belong to a community like this that is helping or incentivizing you, because there's a program, a platform like this where you work with others, okay, to begin to practice. So get a friend, get someone in the group, okay, to discuss this with, to practice together, to even do combined projects, like solve this problem together. And both of you, or you could pick up any online resources, say HackerRank or any other one out there, to just practice, Okay, but again, I think my major point here is take it easy on yourself. All right, and remember, please don't go for the next interview yet. Don't think about it, the next interview. Don't think about the next big company you want to join yet. Be comfortable in this scheme. Be comfortable with this concept. Once you are comfortable, you will build eventually your confidence. Again, I'll go back to that benefit again. Your confidence, anywhere you are, where you currently are, and where you think you are going, the next interview or the next company you want to join. So please take it easy. I cannot say that enough. Now, my final point on this will be this. If you have questions, we can take the question. How many of you have seen a string? You can type it in the message if you have seen a string, or you know what a physical string is. Okay? No, that is not, someone put a sample string. That's not the string I'm talking about. Have you seen a string? Someone put sample string. No, that is not a string. No. All right. So the string I'm talking about here is the visualization part. Have you seen a physical string? I'm not talking about a programming string, your language string, like sample string. Yes, sample string is. But have you seen this? A physical string. Okay. Akinyele Ibrahim says he or she has. Okay, someone said like a guitar string. Yes, you are close to it. Because yes, you are close to it by saying guitar string. Yeah. What other string have you seen? Physical string used to connect doors. Yes. Good. Good. That's what I'm looking for. Guitar string, physical string used to connect doors. So why I ask that tricky question is because you need to begin to see some of these concepts in your programming as physical strong concepts. So if you hear the word string, okay, it's not just a set of characters bounded by apostrophe or quotation string. Okay, in some cases, it's a rope, a physical rope. And the thing about a rope is that you can make it take any shape, which is why that concept is taken into computing data type. Okay, this type of data is string because it can contain anything. This variable can contain anything. It can be alphanumeric, number, alphabet, all right? There is no mathematical operation on it. So if we need a math operation, then we have a data type of int, float, depending on the precision, double, currency, okay? So note it's a trick question to you. Visualize. Again, I'm going to build your intuition through visualizing this. When we get to linked list, stack, queue, hash table, you are going to be doing a lot of visualization, like see them physically. All right. If you are going to buy Legos, go buy Legos, go buy bricks. Thank you. I've taken so much time. If there's any question, please, we can discuss on Slack, or if the moderator think I have maybe 1 or 2 minutes to take the question, I'll just take it. Thank you, everyone. At this point, I hand over the baton, if there's no question, to Shay.
All right, thank you so much. I don't think there are much question for you, so I think it's something that we can just maybe people can start putting out their questions after the end of the call. We can just have a question and answer session for everyone. So I think Shay can go next now. Thank you.
Hello. Good morning, good afternoon, good evening. Thanks so much, Mr. Soji, for that introductory session. And I'm going to be continuing from where he stopped. I'm going to be taking us through big O time complexity and time and space complexity and big O notation. So let me share my screen so we can get started. Sorry guys, I need to quit my browser and reopen it for some permissions. I'll join back shortly. Sorry about that. Let me just get this started. Good. 1 second. Okay, so can you all see my screen?
Yes,
we can see it.
Yes,
Yes, I can see it.
Awesome. So yeah, let's get started. So I'm going to be taking the second portion, and that has to do with, let me start the slideshow. Perfect. So I'm going to be taking the second portion, and that has to do with big O notation and time space complexity. Please, can we just, before we continue, can all of us just ensure that our mics are muted so that we don't distract other people? Thank you. Okay, so what are we going to be discussing today? We're going to be talking about time-space complexity. We're going to be talking about why it's important. We're going to be talking about how to analyze it. We are then going to move on to big O notation. So big O notation is a way of calculating the time and space complexity of an algorithm. Then I'll move to the theoretical considerations and then the real life considerations. So I've tried as much as possible to explain this in a very intuitive way and stay away from a lot of mathematical complexities that you usually encounter if you go read Pigo in a textbook or you take an algorithms course. Okay, so who am I and why should you listen to me? I'm currently a software engineer at Google, and I've been in tech for about 9 years now. I started off as a network engineer, I moved on to cloud and systems development, and now I'm currently a software engineer. But the key parts I really want to emphasize on is that I'm mostly self-taught, and I understand the hurdle that people face when learning technical concepts, especially data structures and algorithms. I really struggled when I was trying to make the switch, and it was very difficult. And a lot of this was because I didn't really have someone to really explain things to me in a very intuitive way. Most times when you take a course, it's very theoretical, or it's shrouded in a lot of mathematical complexity if you read an algorithms textbook. And I also understand how difficult interviews can be. I understand the pain of having to do something you don't think will be useful in your day-to-day job. But I have good news for you all. Understanding data structures and algorithms, as my co-instructor said, is very important. And I'll outline some examples where understanding how these things work under the hood are very helpful in terms of how you build applications in the real world. So most important takeaway here is I hope to help build your intuition about the data structures and algorithms so that you can really understand it at an in-depth level and really understand what's going on. And that will help aid your learning, and you can apply that in other aspects as well. Okay, so let's move forward to our first section, which is time and space complexity. So I'm going to take us down a memory lane to like a computing execution model. And this is, the reason why I'm doing this is I want us to really understand why we are doing all this. Like, I want us to really get an intuitive sense of what is really going on and why do we have to study time and space complexity. So let's say we have a happy user, he writes a program, hello world, just a basic program, and he stores it on his hard drive, or he stores it on his or her hard drive. Now that is stored in cold storage. Cold storage is like our hard drives, our SSDs, that is just stored in cold storage. And the program is typically compiled and stored in storage. Then I'm going to simplify it here because I know some languages could be interpreted for those that are like more into interpreted languages. But the key point here is we have a program that is stored in storage. Now, when that program needs to be run, the operating system needs to run that program somehow. What happens is it takes that program and it loads it into memory. Then when that program is in memory, it executes that program on the CPU, and there's a back and forth communication between the CPU and the memory in terms of when the program is running. So for instance, you want to print hello world. For instance, it goes to memory, it reads the line, it prints hello world, and then the CPU does that computation, contacts the necessary output devices, which is not really necessary here. But the key point I want to stress here is there are two factors involved when you're running a program. Where the program is stored and the operations that run on that program. So how much storage does the program use during execution? Some people have their hands raised. Do you have a question? Okay. So how much storage does the program use during execution? And how long does the program run during execution? These are the two critical points we are answering. Note that the storage we are talking about does not take into consideration the size of the program itself. We are really concerned about when executing, what is consumed during the execution of the program. And this becomes very important because it helps us characterize it helps us know the requirements our programs need, and it also helps us compare different programs to see which one is better when they achieve the same thing. Okay, so I move forward here. Okay, so I'm going to now I want to just use an example so that we kind of understand why all this is important. So let's say we have a dictionary. Dictionary has about 1,000 pages, for instance, and we are trying to find the word in the dictionary. Normally, as an intuitive person, you just open any page, right? You look at the first letter, and you say that, okay, this is maybe you're an A, you're looking for Z. Then you just keep opening till you get to Z. That is you using your intuition. But when you want to describe it as an algorithm, you can't use intuition to tell the computer what to do. It kind of has to have a defined step-by-step way of knowing what to do. So one way we could do is we could just open the first page and start searching for the word. Right? We could just open the first page and say, okay, let's just start searching for the word. If what we are looking for is in the first page, yeah, we'll see it quickly and we are happy. If it's at the last page, then we are going to spend a long time opening all the pages in the dictionary. So that is one way. That is an algorithm, for instance, that we could use. Another one we could use is we could say, okay, if that doesn't work, since we know that dictionary is sorted, right? If I just open the dictionary in the middle, based on what I see in the middle, I can know which side of dictionary to go to. So if, let's say, I open dictionary in the middle and I land at M, and let's say I'm looking for B, I know to go to the left side. Now, note that when you do that, you effectively cut half of the dictionary away from what you're searching for. Now, if you keep repeating that process and you keep cutting half of what you're searching for, you eventually get to what you're looking for. And that is another algorithm. Now, all these things do the same thing, but they do it in different ways. And it's kind of clear that the second one is faster than the first one. Now, we'll talk about these things later, but the first one is something you call like linear search. The second one is something you call binary search. But that is something we'll talk about later. But then if we even want to optimize this further, we could say, hey, since we know all the words in dictionary, why don't you just build like a table of contents where we have all the words and the pages they are stored? In that case, if I'm looking for a word, I just need to go to the table of contents and I find the word immediately. But notice we did something there. We added extra space to store the table of contents. Now that extra space we added, right, will increase our space complexity. And that will enable us to reduce our time complexity in this case. So this is a theme we'll see going forward, where time and space complexities are kind of two sides of the same coin, where if you increase one, you decrease the other. And if you increase the other, you decrease the other. So this third method I talked about is a hash. It's like a hash table, a hash map. And these are things we'll encounter as we go on in the program. But the point I'm just trying to make is it's very important to know how these three methods perform, because they all achieve the same thing. So one could take us 100 years, one could take us 1 day, one could take us 2 minutes. But how can we characterize these things and know how they perform under different conditions? And that is the crux of what we are going to be handling today. So the first example I'm going to be taking is a very simple example. And this was something that happened. There was a very intelligent scientist. His name was Gauss. One time when they were in class, their teachers asked them, I think they were disturbing the teacher, as the story says. And the teacher asked them to sum the first n numbers. So if it's n equals to 5, you sum 1 plus 2 plus 3 plus 4 plus 5. So the teacher wanted to punish them and give them a high number to start summing. Everybody was writing and trying to calculate it, and then Gauss raised up his hand and gave the answer immediately. Interesting. The teacher increased the number again to 1,000, from 100 to 1,000. Again, within a minute or two, he gave the answer immediately. So what happened was Gauss was very smart, and he devised the formula to make that a mathematical formula instead of trying to add up everything. And I'm going to be pulling up something to show you guys, like just as a motivating example. Sorry about that. Okay. So can you all see this Jupyter notebook? Yeah. So essentially, there are two algorithms here to do that operation. The first one is what everybody would do. 1 plus 2 plus 3 plus 4. I should zoom in. Okay, 1 second. Is that better? Yeah, good. So the first step is like, okay, 1 plus 2 plus 3 plus 4. That's what anybody would do. Okay, so the first step will mean 1 plus 2. That's what anybody would do, right? But then there's actually a formula, and it's a formula that I'll describe later. But that formula can give you the answer immediately. So the first algorithm I have here is the first general one that anybody would do. The second one is the one that gives the answer immediately. Now, what I want to show us is, so when I run the first algorithm now, both of them are correct. But notice this, when I increase the inputs, the first algorithm takes so long to compute because it's going to 1, 2, 3, 4, 5, 2, whatever number I have there. I think it's 100 million or 10 billion, whatever. And it's trying to figure out what the answer is. Now, you notice that when the input was very small, it didn't really matter which algorithm I'm using, because when the input was small, it gave the answer immediately. But now I've increased the input, and now it's taking time. Oh, it gives us an answer, 5, whatever, a very large number. Notice what happens when I run the second algorithm. It gives me the answer immediately. So why is this algorithm giving me the answer immediately, and why is this one taking time? And how can we characterize it? How can we represent that in something that is not just about, like, it's not just empirical? Because obviously from empirical analysis, you can see that one is faster than the other. But if you are talking to people and we want to like express the algorithm, how do we do that? This is where time and space complexity comes in. So back to the slide. I hope I don't have to. Okay, good. So back to the slide now. So this is the crux of time and space complexity. How fast does this program run? And how much space does it consume? Again, when we say how much space does it consume, how much space does it consume during execution? That's what is key. And how much time does it, how fast does it run during execution? So one way that I've done is just to do an empirical analysis. We time the program and see how fast it runs. But there's a problem there. How do we make sure we're comparing apples to apples? The execution speed of the program is dependent on many factors. You have your program, you're going to compile it, or you have an interpreter, then you have to now translate it to like machine code that depends on the instruction sets. Then you have your CPU, which determines how many operations it can run. Just too many variables. So the thing is, execution speed depends on a lot of factors, which are related to where the code is executed. But we can't depend on that because it's not scalable. We need a platform-independent and language-agnostic way to analyze programs. And that's where Big O comes into the picture. So Big O is essentially just is a notation, meaning that it's a way for us to analyze time and space complexities. And this was developed by mathematical folks. I will try and steer away from a lot of the mathematical aspects, just to try and explain it in an intuitive way. And then later I'll bring up the mathematical aspects for those that are interested. You can feel free to skip it if you want to. The reason why I include it is because if you are doing studies, you are reading online or reading a textbook, you're going to come across these things. And it's good to just have an idea of what they're talking about. So Big O notation is a way of describing the efficiency of a piece of code, which is usually a function since we group codes into functions. So it helps us have a standardized way of answering the two questions I said earlier. How much additional space does it consume, and what is the time complexity? So the key thing to notice is that once we know how fast a function is, then we can compare it to different functions, and then we can know which one is faster or more efficient. And then that can aid us in what we're choosing. Okay. So how do we do this? What is the mechanism of doing this? So usually, the first step in understanding this is to do a counting analysis. So a counting analysis is a way of looking at a piece of code, trying to estimate how many operations are done to run that piece of code. Now, how the operations tie into the time is that a CPU can exhibit only so many operations in a second, which is known as the clock rate. So using the number of operations your code needs and the number of operations a CPU can execute in a second, you can kind of have an idea of how long your code will run. So the thing about the Big O is that it makes a lot of assumptions about how codes run. For instance, mathematical, relational, and assignments and return statements, they all count as one operations. In reality, it's not one operation, but Big O just abstracts them out and makes them one operation. The idea behind this is if you're adding different numbers, right, that operation is constant anytime you're doing an addition. Almost constant, but not entirely true, but for the sake of big O, just assume it's constant. So in reality, there are multiple operations, but from the perspective of computing big O, they are constant. So we ignore those details and focus on what is important. Okay, so now I'm going to run through a couple of examples, but I'm going to use a Jamboard to try and build the intuition of how we arrive at these things. So I'm going to start with the first example I gave. So let me share that board. Oh, sorry. Yep. Okay. So this is the first example here. So let's look at this piece of code and how do we determine the times complexity? What are the things we look at when we want to determine the time complexity? The first thing that we observe here is, okay, this is a function. And so a quick note, please. I understand when we did the survey, we discovered that a lot of folks were more on the beginner to the intermediate level. So advanced folks, please bear with me. We'll get there, but please bear with me on this introductory part. And the other thing I wanted to clarify is languages in context of learning algorithms, languages don't really matter. So sometimes what I might be describing might look like Python, sometimes it might look like JavaScript, sometimes it might look like Java, C++. It's just for us to convey the point across. That's one very important thing. So now this is an algorithm to sum numbers to n. Sum is equals to 0. So this is basically, I'm doing a for loop, looping through all the numbers from 0 or 1 to n, and I'm summing them into a variable and returning the sum. So how do we analyze this code? What do we do? So, okay, somebody has his hands raised. Do you have a question? Okay, we assume that was just a misclick of the button. Well, let me know if you have a question, or you can type it in the chat. The first thing we'll first look at here is on the first line here. So in regards of the language, the language is not really important. This is Python, because that's what I used to run the example, but the language here is not really important from what I want to explain. I want you to focus more on the steps that are being done, because this could be written in any language. It's not really tied to the language, but it's Python. Okay. So, actually, I lied. This is not Python. This is a mixture of Python and Java or JavaScript, because Python for loops are a bit different. I lied. So I actually wrote the code in Python, but then I wanted to show the language indifference. Exactly. Whatever. Python will tell you church of Java, C++, whatever you call it. Yeah, exactly. So let me see. Okay, so I have my pen. So now we have this line here. Sum equals to 1, 0. What are we doing here? So if we look at it concretely, we are doing an assignment statement. That assignment statement is one operation from an assumption of big O. So this is just one operation. Now look at this loop here. We are doing something in this loop. We are doing an initialization. The initialization only happens once. And then we are taking I and we are moving it from I to none, increasing by 1. So essentially, I takes the following parameters. I takes 1, actually 0, 1, 2, 3, 4, 5. Let's assume n is 5. Let's just assume n is 5. Right. So now the key to note here is this I, this I takes a certain number of values n times. So essentially what we are doing here becomes, let me write it out and I'll explain it, just bear with me here. What we are doing here, we have one initialization. The initialization is only done once when we set I to 0. Now we do a comparison when we do I less than or equal to none, and then we do an increment. We do those n times. Now, for people that are more advanced, you will know that it's not really n times, it's n minus 1 times in terms of the comparisons. But for the sake of big O, those details are not really important, which, as I explain more, you get what I mean. So we have one comparison, right, and one initialize and one increment. And we're doing this n times. Num times, actually. Num times. I'm calling it num for now. We are doing this num times. Num times. Now, if you look at the next line here, what are we doing here? We are doing two things. We are doing an addition operation, and we are doing an assignment operation. An addition and an assignment. Right? Addition and we are assigning back to the variable. And we are doing this how many times? We are doing this num times. The reason why it's num times is because it's in the loop. And remember, we are executing that loop num times. And then when we come to return sum, we do this one time. So if we add up all this together, here, let me go back to the slide. So if we add up all this together here, we essentially get 4 num plus 3, which is O of num. Now I use num here to illustrate the points. Typically you see O of n, O of m, O of m, but those are arbitrary. It's basically what your input is, and your input could be anything you call it when you are doing analysis. But most times you see O of n, O of m, O of whatever. But as we analyze multi-factors and algorithms, you will see that it's not always n, and sometimes there are multiple variables in here that we need to take into consideration. Okay, so in that case, we have 4 num plus 3. But again, when we are analyzing for time complexity, we don't care about the constant factors, and we only care about the magnitude. So if it's 4 num, 5 num, 6 num, we don't care. It is order of num. So in this case, the time complexity is order of num, and num here refers to the inputs. And what this means is, as you increase your num, it takes more time for the code to run. You notice when I put num equals to 5, it was very fast. Then when I increased it, it took time. So that tells us that the time complexity varies with the inputs. And as the input increases, the time complexity also increases linearly. So this is what you call linear. I'll go over the complexity classes later, but this is what you call linear time complexity. Now for the space complexity is usually easier to analyze, but I won't be able to generate a lot of examples where you have a lot of complex space complexities, but as we learn more data structures and algorithms, you begin to see it pop up. Essentially, what to do in space complexity is you look at all the variables you are using. Okay, so we are using sum, right? We are using I. But if you notice, if we increase num, sum doesn't change, I doesn't change. And why is that? Because num is just an integer. And an integer is a fixed size. It's a fixed size value. So if you are storing 1 and you are storing 500, it's still the same size it takes on the computer. Because it's a fixed size value for an integer. Generally. So because of that, the space complexity is constant. So I just want to know, are folks really clear on this example? Because it's important to understand these basic building blocks before we begin to move on to more complicated examples. So just thumbs up if you are clear, thumbs down if you are not. Okay, so I see some thumbs down. Okay, let me see. Let me see what the comments are. Yeah. Okay, so for the space complexity, I will start from questions. Okay, how did that? So you don't understand. So the space complexity, essentially, you look at all the variables that you are using, and you see whether they increase when you increase the inputs. So if you look at the variables you are using here, we are using sum. Sum equals to 0. Sum is an integer. Sum never changes. It could be an integer, it could be a float, but it never changes when num changes. The size doesn't change. I mean, the values change, but the size doesn't change. So if we increase num to say 1 million, it's still 32 bits or 64 bits. And sum is still going to be 32 bits or 64 bits somehow. So that value doesn't change. It's still the same thing we are storing in that space. It's still the same space we are taking to store data. So that's with the space complexity. Then okay, someone has their hands raised. Hello? Okay. So how did you adopt the norm? Okay, so I'll explain again. For the first line, we have one assignment operator. Where sum equals to 0. We have just one assignment. And assignments are constant. That's why I used 1 to represent it. It means it's constant. For the second line, we are doing a couple of operations. We are doing one assignment operation. Once, we are doing only one assignment operation. But then we are doing one comparison and one increment n times, norm times, sorry. So that's why you have 1 plus 1 times norm. Because you are doing one comparison and increment, but you are doing them together n times. The assignment operator is only done once. The assignment operation is only done once. That's the I equals to 0. That's why it's not in the bracket. And then for the sum plus equals to 1, we are doing an addition and we are doing an assignment. Because sum plus equals to 1 essentially means sum equals to sum plus 1. So you first sum plus 1, do an addition, then you do an assignment into a sum variable, which is another constant operation from the assumptions of big O. And all that is in a loop. And we have to multiply it by how many times we do the loop, norm times. That is why we have 1 plus 1 times now. And then for the return sum, the return statement is just a constancy. We're just returning something, and that's why it's 1. So when we open this up and we add everything up, we get this formula here, this number here, 4 norm plus 3, which is of the order of norm. So okay, so I've tried as much as possible to explain again. Let me just get some thumbs up for up if you are clear, down if you are not. Okay, I don't see a lot of down, so we are considerably making progress. But please, the Slack group is open. If you feel that there's a question you want to ask, you can just throw it in the Slack group so that we can like address those questions. Okay, so I'm going to be moving on. Okay, so now this is a much simpler one. This was the second algorithm. Actually, it's actually a formula. It's a mathematical formula where it's like n into n plus 1 over 2. I'll go over that later. But from an analysis point of view, what are we doing in this function? Okay, we are doing norm plus 1. We are doing an addition operation. We are doing a multiplication, and we are doing a division, and we are doing a return, all in one statement. So that's why I have this 4 here, 1 plus 1 plus 1 plus 1, which is 4. 4 operations. And because it's, like I said, is 4, but big O, we don't really care. We care about the magnitude. Any constant can be seen as O of 1. So in this case, we just know that this is O of 1, and this is like constant time complexity. What this means is, no matter what the inputs I pass in, the time complexity is not going to increase. In an ideal world, this is what we'll have. This is the best you can ever get. Like, this is the best you can ever get. But in reality, it's not always possible. So in terms of the space complexity is the only variable we have here is null, and it's constant with respect to the input. So it's just constant space complexity. Okay, so thumbs up if you get this example, thumbs down if you don't. Perfect. I don't see. Oh, I see 1 thumbs down. Okay, so I'll explain again before we move on. We are trying to evaluate how much time we use to run this algorithm. But the thing is, if we look at the line where we are returning the statements, we are doing a couple of things here. So we are doing a multiplication operation, we are doing an addition operation and division operation. And from the perspective of big O, all those things are constants. They are all constant time. And the return statement itself is also constant time. So when we add all those things together, we get 4, which is O of 1, which is constant. Now, I also want to note something here. I'm doing this analysis, but when you do your analysis, you might not get the exact same numbers I get. What is important is that you get the same magnitude. Like if I get O of n and you get O of n, we are good. It doesn't matter if mine was n plus 5 or 2n plus 3. Once n was there, you're good. This is just to build your intuition into how to look at these things and how to like look at code to know what the time complexity is and space complexity is. I hope that clarifies. Please thumbs up if you get it, thumbs down if you don't. Okay, so for those that don't get it, if you could post what you are particularly unclear about, either in the chat or in the Slack, then maybe we can go from there. Okay, so it does not mean the array length. No, so in this case, num is just a number. Num is not the array length, it's just a number here. We are not talking about any arrays now for now. It's just a number. So O of 4 became O of 1 because in big O, we don't care about the specific numbers. We just care about the order of magnitude. So even if you get O of 10, O of 20, O of 30, as far as there is no variable there, it's O of 1. So how is num a constant? So num is not constant, right? Num is passed in, but the constant, okay, I see the confusion. So what is happening there? We are passing num into the function, but as part of the function computation, we are using the same num that was passed in and returning it. You get, so num is not really a constant, but the time it takes to do the computation is a constant, and the space num takes is constant no matter what you pass in, because it's a variable. Do you mean time and space complexity we have the same answer? No. Time and space complexities do not always have the same answers. In this case, in the last example we had, they didn't have the same answer. They don't always have the same answer. Sometimes time complexity is higher than space complexity. Sometimes space complexity is higher than time complexity. Okay, let me see. I love we have another example that gives a different. Okay, let me see. Okay, so just post any comments. If I will try and get to it. So I'll be moving on now. If anybody's not clear, you can. Yeah, sure. I'm going to go through multiple examples. Yeah. Make a comparison between the first and second example based on num. Okay, so in the first example, right? The first example uses a different algorithm, right? And we use num to know how many times we are iterating, because we are summing to num. So we start from 1, 2, 3, 4, 5, 6, 7, up to num. And in the second example, we are using a formula that uses num, but we are not using a loop. We are just using num exactly. We are just using num and plugging it into a formula and getting our answer immediately. So that's why it's constant. I'm having issues with grasping what Pico is. Can you recommend the text so I can find it? Yeah, sure. I'll have at the end. I have some recommended things you can go through if you want a deeper understanding. And you can also post in the Slack chat as well if for any doubts you want to clear. But for now, I think I'll move on. Hopefully it will become clear as I move on to more examples. Okay, so we have this piece of code. I'm going to move back to the, sorry. I'm going to move to the Jamboard. Where are we? Okay, I think it's the same thing I'm looking at here. Yes. So we have this piece of code here that I want to analyze the time and space complexity of this piece of code. So now we have like a for loop. So if you look at it, first and foremost, we have like a for loop, and we have some assignments to variable A, and then we have a for loop here with another set of variables and assignments to B. Now, the thing to keep in mind here is there are two variables here. There's N and there's M. So definitely they mean different things. We don't know what they mean, but they mean different things. So if I take a look at the first line, right? What amount of work am I doing on this first line? I'm basically doing two assignment operations. A equals to 0, B equals to 0. So that's two assignment operations. Now, if I look at this loop here, now you may begin to see a pattern coming up in that when you have a loop, it seems like you're turning to M, but that's not always the case. So if you look at this loop here, we have an initial assignment, which is 1. That's the initial assignment. And then we have comparison and increments, right? Up to n here. And from our previous example, that's 1 plus 1, n times. We are doing this n times. Sorry, 1 plus, it's an addition. Sorry, thanks for bringing that up. Then for the one inside the loop, how many times are we doing this? We are doing an addition and we are doing an assignment. Again, here, one addition and one assignment. And we are doing all this n times because we are within the loop. We have to look at the total amount of work done on that line because it's in a loop, and once that statement is done, it will get done again for the second iteration of the loop, third iteration of the loop, fourth iteration of the loop, till the loop terminates. So essentially, we can look at it and we see that, okay, this piece of code is similar to the upper piece of code. So we can know that, okay, we are probably going to get the same thing because we have J and we have J to M and J plus plus. So this is going to be 1 plus 1 plus 1n. And this is going to be 1 plus 1n. So I'll go back to the slide now. I said n. Actually, this is m. My bad. This is m. 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 Yeah. Yeah, m, yeah. So if I go back to the slide now, we see that what exactly what I was saying. So this 2 assignments, that's why we have 2 here. We have 1 assignment, we have 1 increment and 1 comparison done n times. We have this and then it reduces to this. We have 1 addition and 1 assignment here done n times, reduces to this. The same thing here is what happens in the second part. It's just that the variables are changed. And when we add them up, we get this expression, 4n plus 4n plus 4, and it's order of n plus m. Because I said in big O, we ignore the constant factors and we look at the ones that are the highest order of magnitude. I believe this plus plus is equals to this. Yes, you are correct. It's essentially the same thing. And that is addition and reassignment. Yes. And I indicated that by increments, but you are correct. If you want to add another one in your analysis, you are fine. We will arrive at the same result. So instead of 1 plus 1, if you want it to be 1 plus 1 plus 1, that's fine as well. We will arrive at the same result. Yeah. So that's how we get O of n plus m here for this particular one. So the reason why I took this example is, here is we have 2 variables, n and m. They are not the same thing, right? If we had n and n plus n, it will have been 2n, which will have been n. But because m is different, we don't know what m is. M could be bigger than n, or m could be smaller than n. So we have to include those variables if we are not sure what the variables are. So that's why we call this n plus m. And time complexity is n plus m. For the space complexity, if you look at the entire thing, what are the variables used? A, B, A never changes with respect to n. So the space is increased, but from the perspective of the input, the space doesn't change as we increase the input, which is key to what I was saying earlier. It's when we talk about space complexity, we are looking at the space as the algorithm executes, not the space that is static. The variables all have an assigned space, but as you change the inputs, in this case, which is n and m, the space remains constant. It's because the increment is happening in n plus m, so they are under. Okay, so if someone was asking someone, okay, so that's fine. So that is essentially the analysis of this one. I hope it's getting clearer now. Let me see. So thumbs up if you good, thumbs down if you're not. So space complexity is not always O of 1, but in all our examples, they've been O of 1. And it's kind of difficult to bring an example that is not O of 1 without understanding some data structures, which I don't want to like make things I want to build things slowly. We'll get there. We'll get to your space is not O of 1, but for now it is. Okay. Perfect. So let's move on to the next. Okay, now we are getting into more advanced examples. But please, these parts are very important. These are the basic things we need to, I really want folks to understand. So here is O of 1 because of difference in the variable. So it's O of 1 because the size the variables consume do not change as you change the inputs, which are n and m. So let me give an example. If n is 1 and n is 1, the size of the variables are not going to change. If n is 1 million and n is 10 million, the size of those variables are not going to change. So yeah, because exactly, they're the same data type, correct. Perfect, they're the same data type. Yeah. So I know some folks that in some languages that are a bit more, that have some nuances might disagree with me. But for the sake of for the sake of just analyzing generally, let's just agree on that for the more advanced folks. Yeah. Let me see. So counting and so I'm going to go through another example now and bring up some differences. So for the next example, so we have this piece of code. What is going on here? So we have two for loops. So just a hint. Once you see a for loop, you know that okay, you should be looking at linear complexity O of n. That's kind of what you look at, but it's not always the case. But those are some ideas you can start building on. Now we see two for loops. My intuition tells me that okay, if we have a for loop that is looping to a certain number, and another loop within that loop that loops to a certain number, that's kind of like number of times of the first loop times the second loop. That's just a base analysis. But again, we have to look deeply and see whether it's really true. Now, as you begin to practice more and more, you begin to build an intuition for it where you can look at it and you can know, okay, this is this and that is that. And we'll build those patterns as you go on. So for this first one here, we have two assignment statements, A equals to 0 and B equals to 0. So this is 1 plus 1 essentially, which is 2. Now, for the second loop here, I hope you can kind of see a pattern for me here with the loops we have been analyzing. So I'll just go straight to the answer. If anybody is not clear, let me know. This should be kind of clear from what we've done earlier. I'll iterate it again. We have an initial assignment statement, I equals to 0, which is the first part. Then we have a comparison, an increment, which is done n times. Now, in this inner loop, things begin to get a little bit interesting. It's essentially the same thing we have up here. Because if you look at it, the structure is the same. So we have one, right? We have one assignment. And so let's just analyze the loop on its own. And we have 1 plus 1n here. Now we analyze the loop on its own. But the problem is that loop is within another loop. So we have to multiply all this n times again. So things get very interesting at the second loop. Now, if you look at this line of work here, right? Actually n times because it's n, not m. Okay. So if you look at this line of work here, it's essentially what we've done before. One addition and one assignment. But now, we are not just doing it n times because it's within this loop. We have to do it n by n times because it's within the nested loop. Yes, exactly. Nested n time, correct. So now, for this one, this is kind of what we've been seeing before. 1 plus 1n. Yeah, this is kind of what we've been seeing before. Right? And this one is kind of what we've been seeing before, where we have 1 plus 1n. Again, please, I want to reiterate. When you do your analysis, you might not get the same 1 plus 1 I'm getting now. You might get 2, you might get 3, you might get whatever. The most important thing is that the order of your n corresponds. And take this into consideration. So when you are going to like study and you see all this analysis, you might not get exactly the same analysis they're getting. That's fine. Those details are different. Different people may analyze it in different ways. But the order of magnitude of n should be the same. Yeah. Okay, so if we take this now and add it up, right? We get what is happening here again. Let's go back. So on the first line, we get 2 assignment statements. On the second line, 1 assignment, 1 increment, and 1 comparison done n times. We are familiar with this. For the third one, now when we break it down, we have 1 assignment statement. Normally, it should just be 1 assignment statement, right? But now, because we're in the loop, we are doing that 1 assignment statement n times, right? And we have 1 increment and 1 comparison now done n times normally, but now n by n times. And for within the nested loop, we have 1 addition, 1 assignment, but we are doing that n times. Can you explain the magnitude of n to me like 12? So magnitude of n means basically like n squared, n cubed. So in this example now, we see that we have an n squared when we are summing up. Let me finish. I'll come back to it. I'll come back to it. So for the second loop down, I think this should be pretty straightforward from what you've done before. So now if you add up all the terms here, you discover that you start having n squared somewhere, n squared here, n squared here. And then when you add everything up, you get this this formula here, which is not really important. What's most important is you have n squared and you have n, right? And then again, from big O, we don't care about constant values and we care only about the highest magnitude. So if you have n squared plus 10n plus 50n, we don't care about the lower orders. We only care about the biggest order. The reason why we care about the biggest order is as the input begins to grow large, that is what is going to matter. Yes, correct. The one with the highest power, yes. In this case, the one with the highest order or the one with the highest magnitude. You understand magnitude as you go on. But in this case, the highest power is the highest magnitude. So our time complexity here is big O of n squared. And our space complexity here is constant because if you look at it, they're all integer variables. We don't have any special things done here. So that's why the space complexity is constant. So back to a question here that said, can you please explain the magnitude of n? So we'll get to magnitude of n later. So this one, I know it was a bit more involved, but I hope people were able to follow along, and please thumbs up if you good, thumbs down if you're not. Okay, so for thumbs down, please ask your questions in the chat. Why is there no m here? Because it's so n. That's the reason why I'm changing these things is because they are arbitrary. They can be anything. You could have 2 n's, you could have m and n, doesn't matter. What just matters is that there are 2 different variables or they are the same variables. Those are the things that matter. Yeah, because the second loop is dependent on n. Yeah. Could you shed some light on space complexity? So for space complexity again, it's about what. Okay, so the space complexity is what as my input grows, what additional values are my function storing? Yes, I will share the slides. What additional values are my function storing? Now, if your inputs are integers and all what you are storing are integers, it doesn't really matter if you're passing the highest integer. An integer is always going to be 4 bytes. If it's double is always going to be 8 bytes. It doesn't matter if it's like the highest double you find. So that's why it's constant now. As we begin to analyze data structures, we begin to see that it's not always constant. So to say. So for the nested loop, so the nested loop is essentially a loop inside another loop. And because a loop normally executes, say n times, the outer loop executes n times, that means for each of the n executions, the inner loop will also execute n times. So if you kind of look at the execution, let me go back to, sorry. No. Let me go back to this. So if you look at the execution, right, let's say n is 5, for instance. I think it's better if I use a text box. So let's say n is 5. I hope you can all see. Yeah. So let's say n is 5. I'm going to go through 1, 2, 3, 4, 5, right? That's what the outer loop will take. But for each of the work I do in the outer loop, right, I'm doing additional work in the inner loop as well. So for this one now, for instance, let me write it this way. So for the outer loop, let's say I have 0, 1, 2, 3, 4, 5. But for each of the work done on the outer loop, I also have 1, 2, 3, 4, 5 in the inner loop, and 1, 2, 3, 4, 5 in the inner loop, like that. So if you look at it, I'll essentially build up a square or a rectangle, and that's where you have, and that's where n squared comes into play. Let me go back to see the charts. What's happening here? Seniors, we'll get to log n. We'll get there. 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 I'm just trying to build intuition so that we'll carry everybody along. We'll get there. We'll get there. It's fine. We'll get there. For time complexity, did you take into consideration yes, I did take into consideration the second part. But if you notice, for the second part, right, because it's of the order of n, the order of n squared has overshadowed it. So that's why we just drop it. Please explain the line 1 plus n. So essentially what you are doing is you have one assignment and one addition, right? Oh, what? Okay, so you have one assignment. The first one on the left is the initial assignment. That is only done once at the loop. Now the 1 plus 1 are done n times because that's where you do your comparison and your increments. Please explain more about the square n squared. So n squared essentially means you are doing something n times. So you are doing something n by n times. That's essentially what n squared means. At what point can we get n squared plus n? So even if you get n squared plus n, you are gonna reduce it to n squared because you only care about the higher order terms. You don't care about the n term. So I think I've tried to answer as much as I can. If there are any other things, you can drop us a chat in the group chat so that we can explain more. But please, if anybody has, I just want to get thumbs up, thumbs down, to just see the ratio of what is happening here. If people are feeling it or people are not feeling it. I know it can be tough to grasp as well, but if you are not getting it, there's nothing wrong with you. It's fine. It's complicated in the beginning. You just have to take your time to understand it. So don't be feel sad that everybody's getting it, I'm not getting it. Never mind. I was once in a class like that, and it seemed everybody was understanding that. I thought I was the only one that didn't understand. It's fine. So can we say the more necessary algorithm is high degree of it? In general, yes. In general, yes. I doubt when more gets in the first try. Well, except maybe from few geniuses, but for the vast majority of like us, no, you don't get it on the first try. You get it after multiple tries. But as the good thing is, as you keep doing it, you keep building on what you did before. So you're not starting from afresh, and then it becomes more clear as you work more examples. High space complexity. So we'll get to high space complexity when we talk about data structures. For now, I want us to do the intuition for time complexity. Okay. So let's move on. Now, I'm going to talk about a very key thing in the analysis, which is the logarithm. Now, the logarithm is usually difficult for people to grasp because people don't really understand what logarithm means. Now, essentially, I'll just say this. What the logarithm of a number says is how many times can I divide it? So in this case, we'll be dealing with log to base 2. So what the logarithm of a number says is this. How many times can I divide the number by 2 to get 1? So what's the log to base 2 of 8? How many times can I divide 8 by 2 to get 1? If I divide 8 by 2 once, I get 4. If I divide it by 2 again, I get 2. If I divide it by 2 again, I get 1, which is 3. Exactly. So logarithm come into place when, remember the first example I gave where you have a dictionary and then you open it at the middle and then you choose whether you want to go left or right and then you open it to the middle of what is remaining, where you are cutting the problem into half. That is logarithm, essentially. Whenever you have a problem space and you are cutting the problem into half, that is logarithm. That is essentially that's the logarithm involved there. But for most of our constitution, we'll be talking about log base 2 because we deal with binary mostly. So now I'm going to go back to the Jamboard and explain how this logarithm is about. Okay. So this is going to be a bit, I'm going to try to take use another way to explain this now. So we have logarithm of a particular number. We're trying to find the logarithm of a particular number, right? So we have n, I equals to n. This is just an assignment statement. So this is 1. Because it's just one assignment statement. Counts is 0, 1. It's just one assignment statement. Now, this is where things get interesting. How many times do we do this? Why I is greater than 1? How many times do we do it? How many times do we execute that loop? Now, it's not really clear because we have a while loop and we are incrementing counts and then we are dividing I by 2 each time. So now this is the problem. How do we know what we are doing? In cases like this, when you are not sure, right? Just use an example. So if I say if n equals to 16, for instance, right? I'm going to execute this 16. It's because I is initially going to be 16, right? Then I is going to be 8. Then I is going to be 4. Then I is going to be 2, right? Then I is going to be 1. Now, if you look at this definition here, actually, we're not going to do 1. Why I is greater than 1? I is going to be 2. These are the values I will take. And this is 4 times, right? 4. So these are 4 values, the total. And if you look at this, this is the logarithm of 16. This is the log to base 2 of 16. So in this case, we are going to do this comparison 1 by log n times log n, which is log to base 2 of n. But for this example, I'll put it in other examples, I'll remove it. Because we are going to do this log n times. Why geometric order for breakdown? Because you are dividing by 2 within the loop. You are dividing I by 2 within the loop. So this one here, we are doing an addition and we are doing an assignment, right? And how many times are we doing this within the loop? We are doing it log n times. Log of n times. For this one too, we are doing 1 division and 1 assignment, and we are doing this log n times because it's within the loop. And for this one, we are doing it once. So I'll go back to our slides and just explain it from there. So essentially what I explained, if you look at the first line, I equals to n, 1 assignment, count equals to 0, 1 assignment. Now, for the while loop, because we are doing it log n times, that is why we have 1 comparison done log n times. And then within the while loop, we please can someone mute their mic if they're not talking? Okay, thank you. So within the while loop, we have this same pattern again. It's 1 addition and 1 assignment. But now we are doing that log n times because it's within the while loop and the while loop executes log n times. For this operation here, we are essentially dividing I by 2 each time. We are having I each time, which was similar to the example I gave earlier. So we are doing 1 division and 1 assignment, and that is done log n times. And 1 return statement. So now if we add up these terms here, we get 5 log n plus 3, which is 4 of log n. So this is essentially what log n means. You are taking a problem, you are breaking down, you are breaking it down by half, or you are doubling by 2 each time. That is essentially what log n is. Why are we using log n for the while operation? I intentionally used it. So we are using it because we are dividing I by 2. If you notice, in the other loops we're incrementing by 1 or decrementing by 1. But in this case, we are dividing by 2. We are no more incrementing. So whenever you are in a loop and you are multiplying or you are dividing, a log is locking somewhere in there. Does +3 mean the number of steps? So +3 is just the addition of the entire thing I have there. I just added everything together. It's just the addition of that column. So log n is less complex or faster than O of n. So O of n is slower than log n. Or log n is faster. is faster than O of N. Yes, I think log N has to do multiplication and division. That's correct. Whenever you have multiplication within a loop or division within a loop, look closely. The log N is there. So if you notice, when we're doing the loops initially, right, we were adding by 1. So we're just incrementing, counting to N. But now we are multiplying or dividing. In that case, we are reducing the problem space by a particular factor each time. By what we are multiplying or dividing by. In this case, it's 2. So yeah, log N locks in there. Log N to base 2 locks in there. We say we are not dividing by 2. So if you're not dividing by 2 and you're just decrementing, that will be N. That will be N in that case. Because you are going from... So a good way to look at this thing is... Okay, so let me go back to the whiteboard. So a good way to look at this thing is, when I have a variable in a loop, right? How many times does that what are the values it takes? What do the values those variable take? And how does it relate to the input? So if you ask yourself that question, you see that here, we take, so let's say we use 16, and we are dividing by 2 each time. We are taking 4 values with respect to 16. If we use 32, we'll take 5 values, like that. So that's why it's logarithmic. So if you are increasing by 2, so if you are increasing by 2 or you are decrementing, as far as addition or subtraction, it's still N. If you are doing any operation and it's addition or subtraction, it's still N. Yeah, it's still N. What if we are multiplying and dividing by a number other than 2? Then it will be log to base 3 of, it will be log to the number of what you are doing. So essentially, a logarithm of a number asks you, so a log to the base of a number, right, asks you, by what power should I raise the base to get that number? Or how many times should I divide that number by the base to get my answer? Like log to base 10 of 100 is 2. Why? Because if you take 100 and divide it by 10, right, you get 10. Divided by 10 again, you get 1. So you have to divide it by 10 2 times to get 1. It's the same thing here with logarithm. It's just that here we are using 2 instead of 10. That's essentially how the logarithmic thing works. So logarithms are very important because, like I said, in the best case, we'll have in the best scenario, we'll have constant complexity, but the real world is not possible. So the best you can get to constant is log, and log appears everywhere. In fact, logs are like, I would say they are the bread and butter of computer science. Like, they are the bread and butter of computer science. So a quick note, I understand that we're a bit out of time because we started late and folks have other things. But since this is going to be recorded, I will still go on. If you can stay, it's fine. If you can't, you can get the recording. If you have any questions, we can attend to those in the group. These are first time. Maybe we'll be more cautious on type management going forward. Yeah. Okay. So what if the variable I decreases by subtraction? In addition and subtraction are the same thing. They are two sides of the same coin. You can go from 1 to n, you can go from n to 1. Multiplication and division are two sides of the same coin. You can multiply up, you can divide down. So multiplication, division, log is locking. Not always, but it should be locking in the corner. Addition, subtraction is usually just normal n analysis. Modulus, that's complicated. Let's keep that. Let's take that offline. That's a bit complicated. That's complicated. Let's take that offline. Yeah. Okay. So let me go back and try and see where we are now. So I hope this logarithm is clear. So it's important we get these basic concepts, please, because these things are going to show up again and again, and they will show up in bigger examples. So you have to get why it's logarithm. Okay. So please, thumbs up if you get it, thumbs down if you don't. Okay. A lot of people get it. For those that don't get it, please, there's nothing wrong. Just post your questions and we'll get to it. Can you recap briefly? Okay, so the reason why, so in terms of what we're doing here for logarithm, whenever you have a problem and you are going through a loop, but you are breaking down the problem each time by a factor, and you are not going by constant value, like you're not reducing constantly or increasing constantly. You are breaking down by a factor, like you are dividing or you are multiplying, then the log is somewhere there. If you are just adding and subtracting through a loop, then it's usually n. So the fastest time complexity is O of 1. Yes, constant time. The next fastest is log of n. Yep. And it's very important to understand it. Like, this is very important. When you get to trees, when you get to graphs, this log n shows up a lot. Like, it shows up a lot. Sorting algorithms, searching algorithms, everywhere. Log n is like kind of what makes a lot of things efficient for us today. Okay. Okay, so now let's go on. So now I'm going to look at another example here. Now this example has to do with let me see how far we have to go. Okay, so we're almost done with this COCO analysis. I'm just going to move on from here and explain a couple of things. So for this example, this is a key one I also want to go over. So let's go back to the board. Okay. Is this okay? This is the example we have. Is it the same thing? Yes, it's the same thing. Okay, so for this one, we're kind of familiar that this is an assignment statement. So this is one assignment statement. Now, for this loop here, this is familiar to us, right? We have one initialization statement, one initial assignment statement. We have that with one comparison and one increment, and we have that n times. This is clear. We are clear with this. Now, within this one here, what do we have? We kind of have the same thing. We have an initialization here. We have a comparison here, and we have a decrement. Yeah. But how many times are we doing this? Is it n times? We are not sure because it's going to I. And what is I? I is taking values from n here. So now we need to do a little bit more analysis here to see what is happening. So essentially, I takes 1, 2, 3, 4, 5. Let's say n is 5, right? I takes numbers 1 to 5. But for each iteration of I, right, we are counting down to 1. All right, we're counting down to 1. So in this case, we don't do anything because we are counting down to, we count down to 1 here. Here, we count down to 1, 2, and 1. I hope this is clear. So within the inner loop, what I'm doing is, within the inner loop, we are counting down to I. We are starting from n, and we are counting down to I. If that makes sense. So we start from n. I'm not explaining this properly. I need to look for a better way to explain it. So we have 0 to n, and we start from n. Okay, so let's do this. Let's take I equals to 1. Right? In the inner loop, what do? We start from n, which is 5, and we count down to 1. Right? Then when it's 1, we don't do it again. What do we do when I is 2? When I is 2, right? We start from 5 and we count down to 2. Because we are counting down to what I is, right? Is everybody clear on that? Now, when I is 3, we count down again to 3. When I is 4, we count down to 4. When I is 5, we just have 5. Now, what does this tell me? This is like half of a square, right? This thing is like half of a square. So essentially, that tells me that this is n squared over 2 times here. So the reason why I brought up this example is sometimes looking at it is not really clear. You kind of have to do some like examples to see how it goes. Now, there are mathematical ways you can solve this, but I want to stay away from using like complex mathematical expressions here. I want to just build the intuition because intuition is very important. And you will see this pattern here forming up a lot where you have these squares, like these squares that is halved in a way. So we do this n over 2 times. I think we are familiar with this one. 1 plus, this is just two addition statements, right? two addition statements plus one assignment statement. And we do this how many times? N over 2 times for the inner loop, right? And N times for the outer loop. And don't forget, I forgot here too, we do this N times for the outer loop as well. I forgot that in the upper one. So we can see that using this now, we can now sum up all these terms and come up with what we have. But just by looking at it, I already know that we have N squared somewhere here. And we have N squared and we have N. So I already know it's big O of N squared. I don't need to go through that detailed mathematical formula. But these are things you begin to see as you proceed. So let's go back to what we have here. So essentially we have one assignment. We have one assignment and one comparison and one increment done N times. And here we have one assignment done N times and a comparison and one decrement done N over 2 times N times. N over 2 for the inner loop, N times for the outer loop. Same thing here, we have two addition, one assignment done N over 2 times N times. N over 2 for the inner loop, N times for the outer loop. Adding it up, we get O of N squared for our time complexity. Again, for our space complexity, our space complexity is the same thing we had before because everything here is constant. We don't have anything incrementing with the input. Now, there's a key pattern I want to emphasize here. This work done in the inner loop is a pattern that is very important. If you look at this formula, this is like N plus N minus 1 plus N minus 2 plus N minus 3 to 1. That's you are summing from N to 1, all the terms from N to 1. It's the reverse of doing 1 to N that we did earlier. They are both sides of the same coin. And this is the formula for that kind of expression, N into N plus 1 over 2. Now, this is a pattern that comes up a lot, and I will encourage you to know it, to know the pattern. And if the pattern is not very intuitive for you to understand, remember the square example I drew. When you have a square, and you have a square that is N squared, if you take half of the square, you get N squared over 2. But big O doesn't care about factors. We only care about the order. So N squared over 2, N squared over 3, N squared over 4, 5N squared, they are all N squared. Thumbs up if it's good, thumbs down if it's not. Okay, we are getting fewer thumbs up. I think we are getting to the crux of the. For sanity, anything nested loop is N squared. Well, sometimes it is, sometimes it's not. You have to be careful. There are some examples where it is not. I will go over them. But most times, yes, they are N squared. You have the whole loop N squared. You are still finding it hard to understand why we are getting N over 2. So we are getting N over 2 because in our inner loop, we are looping up to N minus I. So we are starting from N and we are going to N minus I. But what is I? I is from 1 to N. So we are going from N to N minus 1 to N minus 2 to N minus 3 up to 1. Exactly. So that is how we have that. That's why we have that series. That's the work done in the inner loop. The first time we do N work. The second time we do N minus 1 work. The third time we do N minus 2 work, N minus 3 work till we get to 1. So if you sum up that term of the series, that's the formula there. Yeah. So again, let me see. Okay. My head, yes, I understand this is tough. Like sometimes you might need to go over it again. You might need to go over it again to really understand it. But I really want us to build the intuition behind it because this is very important. The fundamentals are important. Very important. Before we go on to more interesting stuff. So thumbs up, good. Thumbs down, no good. Okay. They are getting more goods. For those that are not good, please utilize the Slack. Would try and as much as possible to get to you all. I thought to be N squared over 2. You are correct, but N squared over 2 is N squared. We don't care about the constant. N squared over 2 is like half N squared. We don't care about the constant. We take them away. We just care about the order of the magnitude. They are going from N to N minus 1, yes, up to 1, which is basically half of it, yes. So if you take N minus 1, N minus 2, if you try and visualize it, you see that each time you are chopping up something from the next level and you are kind of having like a staircase. And that's like half of the square. Yeah. Basically, we take the one with the highest order, right? Yes, you take the one with the highest order here. Yeah. Okay, so I know I've bombarded you with a lot of analysis, but now this is like, take a step back and look at the big picture of what we are doing. So we have different big O orders. We have constant order. Constant is what we've seen. Constant essentially means no matter how much I increase the input size, the time my algorithm will run doesn't change. It doesn't matter what time my algorithm runs. My algorithm could be the slowest. Let me backtrack. It doesn't matter how long your algorithm runs, as far as it doesn't change with respect to the input size. Can we run the mass for 1 plus 1 plus times n over 2? So essentially, you are doing an initial assignment statement for the left one. Then 1 plus 1, 1 plus 1 is the increment and the assignment, and n over 2 is the number of times you are doing the inner loop. Okay, I think what I'll do is I just remember that after the stuff, the chat will not be available. So henceforth, I'll read the question out before I answer them, so that it helps when you are watching the videos. I just thought of that now. So that's constant. For linear, we've seen linear. Linear is usually when you have a for loop, like looping to n, and you are touching every item. Yes, we are sharing the presentation. Logarithmic is what we've seen. You are either you are reducing the size by a constant factor, or you are doubling what you are increasing by a constant factor. And logarithmic is close to linear, and it's almost as good as linear, but it's what they call it. It's kind of the best you can get to linear. To constant, not linear, to constant. Now we have log linear. Log linear is linear rhythmic. Now we begin to combine these big O's together now. So log linear is linear rhythmic, which is n log n. Essentially, it means you are either doing n walk log n times, or you are doing log n walk n times. I'll give an example later. Then we have quadratic. Usually, the simplest for quadratic is you're having 2 loops. If it's 3 loops, n cubed. 4 loops, n raised to power 4. Usually, for you, you have to do a case-by-case analysis. For exponential, exponential is something I don't really want to touch on now. I want to wait till we get further in the course when we are getting towards recursion. But essentially, these are more advanced complexities where you are kind of searching the entire space for something, and you are doing recursion, or you are for factorial, you are doing permutations. Okay, so so this graph essentially shows you the elements. Elements here is as you go from left to right, as you increase the size of the inputs. The operations are like how long it takes for it to run. So you can see that here, the constant factor log n and O of 1, they are almost the same thing. You can't find a difference between the red line and the blue line. They are almost the same thing. You see, O of n is a bit better, trending up. And then O of n log n is the next. That is the next best. And then you can see n squared is just not very good. It goes up. You increase the size of the input small, the graph goes up. Number of operations go up like very crazily. Then 2n and n factorial, they are just not very good. We don't, in fact, for the context of like real life applications, you usually stop at quadratic. All your algorithms are usually quadratic most times. Exponential could come up, but they are usually for very small input sizes. You can see that, in fact, once you begin to get beyond like a certain number of input size, the exponential and factorial become, they are not very useful again. So so let me see. Let's go on. So what are the rules of big O? I've touched on this before. I'm just going to go through them. We ignore the constants because we only care about the order of growth. Then we drop the lower order terms. So n squared plus n plus 1 is just n squared. We don't care about the lower order terms. Now, as n grows large, the reasoning behind this is as you increase n, as n grows large, the larger term dominates the smaller term. So it's like if you have n squared plus n, if you have 1 million, and if n is 1 million, for instance, and you're adding 1 million to 1,000, it becomes very small in comparison. If you now double that, and you're adding 1 trillion to 1 million, it's almost non-existent. So that is why we don't care about the lower order terms. Variables are combined only if they refer to the same inputs. So if I have n plus n, I can't combine them together. But if I have 5n plus 5n, I can combine them to 10n. And then we always assume worst case analysis. I'll cover worst case average case and best case later on. So any questions? Does anybody have any questions? You can type them out in the chat. Okay. So the quadratic parts. So someone is saying, please, I don't understand the quadratic parts. So you can drop more details on what specifically you don't understand, and then we can go over it. I will be interested in the space complexity of the last example. So the space complexity is constant because we don't store anything. The variables don't increase the size as we increase the inputs. All the variables don't increase as we increase n. So the space complexity is constant. Okay, so best case, worst case, and average cases. What does this mean? So the issue here is sometimes the input to algorithm determines how fast the algorithm runs. All right. So let me give an example. If you are doing a linear scan to check if an element exists in an unsorted array, notice that the array is not so. We'll talk about arrays later, but let's say you have a collection of arrays, like sequence of values. I want to check if an element exists. And we start from left to right and search for the element. The best case is that the element is the first element, meaning it's O of 1. If the element you are looking for is always the first element, that's our best case scenario. It's O of 1. The worst case is if it's the last element. So we have to scan through everything and get to O of n. The average case is usually the sum of all the possible cases over the number of cases. In this case, the sum of all the possible cases in this case is 1 plus 2 plus 3 plus 4 up to n. Notice if it's familiar with the other pattern I showed you of n to n minus 1, n minus 2, like that. And we know that sum of all possible cases, that is n into n plus 1 over 2. Number of cases is n. So if we divide it, we still get O of n. Okay. So that is the rationale behind the average case. So usually we care about the worst case. Usually. But sometimes the worst case rarely occurs, and then we'll deal with the average cases. We will talk about those later when we start analyzing more algorithms and data structures. But I just want to put into consideration that you care mainly about the worst case most times, or the average case. You don't care about the best case, because the best case of any algorithm is O of 1. But the worst case is what we care about. What is the worst that can happen to this algorithm? Okay. So this is exactly what I talked about. I mean, I've talked about this already. Constant time complexity. I mean, you can read it later and see. Basically, the key thing here is that the size of the input doesn't affect the runtime. So when to apply best, average, and worst cases, as you go on in the course, you understand when to apply them when you're analyzing your algorithms. I just wanted to make sure that I mentioned it here so that we're aware of it. So constant space complexity just means that what's the case when the algorithm is not found? I don't understand your question, sorry. When the algorithm is not found, I'm not sure. Oh, you mean when the item is not in the list? Oh, if the element is not in the list, then you look through everything. That's the worst case. That's the worst case. Yeah. That's the worst case. Yeah. Nancy, you said quadratic time complexity. No, it's not quadratic time complexity. It's linear time complexity if the element is not found, because you are looping through the elements. It's just one loop. Okay. So logarithmic time complexity, we've talked about this. And basically, it's number of operations done. So in logarithmic time complexity, the number of operations you do increases by 1 if the input size is doubled. So that's the best to constant we can get. When to apply quadratic time complexity? So it comes up when you are doing 2 loops most times, when you have a loop embedded into another loop. So the outer loop works n times and the inner loop works n times. You multiply them, you get n squared. Linear time complexity. When you increase your operations by 1, the input increases by 1. So these are things we've done before. I'll just leave it here. You can go through the slides and ask any questions if you have. Log linear. So log linear in this case means one of 2 things. This is n log n. So it's either you are performing O of n work log n times, or you are performing log n work n times. So it's kind of difficult to analyze sometimes because it's not really clear, but I would bring in 2 things we've done before. and kind of show us how we can analyze it. So let me go to the next example. If I'm going too fast, let me know so that I can slow down. Yeah. Okay. So in this case, right, this is pretty familiar. We just have 3 assignment statements. This is pretty familiar. 3 assignment statements. In this case, we know that we have 1 initialization, 1 comparison, and 1 increment. We are doing this n times. Now, how many times are we doing this in the inner loop? The issue is, if you notice here, we start from j equals to 2, j less than or equal to n, and j is j times 2. So you can see here we are doubling j, which, okay, so someone is saying we can take a break for today. I don't know, the organizers, do you want us to take a break before we continue? Just let me know. Yeah.
Okay, so basically we have plan for each week, and so next week there is another class we have to take. So not to affect that, I don't know if we can just maybe wrap this up today so it won't affect next week's class.
Okay.
Yeah,
sounds good.
Yeah.
So I will try and go a bit faster, and just to explain the main point, I'll go a bit faster. So in this case, because we are multiplying j by 2 each time, we can see that there's going to be logarithmic complexity here. So the same thing we've done before, right? But in this case, how many times are we doing this in the inner loop? We are doing this log of n times in the inner loop. And because it's within the inner loop, we have to multiply by n times for the outer loop. This here is essentially the same thing. We are doing addition, division, assignment, and we are doing this within the inner loop log n times, and then within the outer loop n times. So I won't go over the details of how to add it. It's just similar to what we've done before. But here you can see that we have an n log n appearing in the inner loop and gives us an order of n log n. So that's usually the pattern it takes. So I won't really worry too much about exponential for now. We'll deal with exponential later. I really want us to understand everything up to quadratic. For exponential and factorial, we'll deal with those later when they come up. When they come up, we'll talk about them. Yeah. So for quadratic, we dealt with quadratic. If you have 2 loops, it's quadratic. So a key point here is if there are multiple variables, then you can't combine it together. So if you have multiple variables, you have to list each variable. For example, double loops become O of mn, not n squared. And if you have triple loops, you can have m squared n if they are not the same variables. But if they are the same variables, you can combine them. But again, the presence of double loops does not mean it's quadratic. It's not always the case. You have to analyze it and look at it. It could be log linear, like in this example. We had 2 loops here, but it was log linear. It was n log n. It could even be linear in the next example. Now, this example is a bit on the crazy side, but I included it because this is the pattern you will come across a lot. So I'm specifically choosing the example because they cover all the patterns, all the major patterns you need to know going forward. Once you master those patterns, you'll be able to easily analyze time and space complexities generally, but it might take you time to get them. Okay, so let me go back to how a quadratic would not be, you can have 2 loops and it will be linear. Okay, so we have this, right? We are familiar with this. We have 1 assignment statement. What are we doing in this inner loop here? Looks familiar, right? We start from n, we are going to 0, but we are having I each time. This tells me that there's a logarithmic component somewhere that is in there, right? Okay, so I say fine, this is log. We are doing 1 plus 1 plus 1 here for the initial assignment. We are doing this log n times. But there's a problem. How many times are we doing this in our loop? We are going to I. What is I? Log n. So this requires you to look deeply and build a kind of intuition around it. Because if I assign values now, this is I. What is I here? We don't know. I takes values of not n. I takes values of log n. And what are these values of log n? So let's say n is 16, for instance, right? That means I will take values of 8, right? 4, 2, and 1. So I takes these values, right? So that means our summation is this. This is all the work we are doing in the inner loop. And what is this exactly? What is the summation of this? Well, it turns out that this, if you look at, so I want to build some intuition around this. If you look at 4, right? If you add 1 and 2, you know that is 3. It's 1 less than 4. If you start from 8 and you add 4 to 1, it's 1 less than 8. If you go from 16 and you add all this, this is 15. So please can you mute your this thing? Thank you. So essentially, this becomes n plus n minus 1, which becomes 2n, n plus n minus 1, which becomes 2n minus 1. Okay, I'm fast. Okay, I'll take it slowly. I was trying to go fast because of the time. But I will take it slowly. So let me explain this again. Let me start from the beginning for this. So guys, take it, be patient. It's not, you might not get it immediately, but with time, with practice, watching the recordings again, I'm hoping it to make a lot of sense. So the crux of the matter here is this. What is the amount of work we are doing in this inner loop? We are going from j to 0 to I, right? So I take some values. We don't know what I takes. So the first thing we need to figure it out is, what are the values that I take? So when we come here, we see that I is halved each time. So if n is 16, I will take 16, 8, 4, 2, 1. These are the values of I. And we are now asking the question, what is the summation of this with respect to 16? 16 is n. So let me just put it here that n is 16. Let's be clear. So what is the summation of this? So without doing too much math, just looking at this on its own, you can see that all the lower terms here, they sum up to n minus 1. So that's why this is n plus n minus 1, which gives us 2n minus 1. But we don't care about the constant terms, the lower terms for Pico. So we say it's 2n, which is essentially n. So that's how we arrive at having O of n work done here. O of n work done here. Yeah. Totally in the inner loop. But there is something here that we need to take into consideration. We've accounted for the fact that this is the total work done in the inner loop. So we don't need to multiply it by log n again. I hope that's clear. Yeah, okay. So the same thing here, we do one addition, one assignment, and we call this n times. So if we add up all this, we see that n is the highest term and we have O of n. Okay, so I'm going to recap. The crux of the problem here is, what is the amount of work done in the outer loop? What is the amount of work done in the inner loop? The amount of work done in the outer loop is straightforward. We know it's log n because I is halving itself each time here. And we know that whenever you have division or multiplication where I is halving itself or multiplying itself, that's log n. Now, what is the amount of work done in the inner loop? Now, the amount of work done in the inner loop is a little bit complicated because we are going from 0 to I. But what is I? I is half each time. So remember then we had the sum of a square where we had this and we had half of it. Where we had the square and we had half of the square. Because we were going from, let me let me bring up that for my example. I think I have the example here. Remember this example where we're going one down? We're going 5, 4, 3, 2, 1. But in this case, we are not going linear. We are not going by subtracting 1. We are going by halving. So that's why we have it being halved each time. So this is the amount of work done in the inner loop. And then when we add everything up, we get this formula here, which is n plus 1. And it's essentially 2n. And that's how we get n in the inner loop. So this pattern will come up again in future. So that's why I included it here. I know we are getting tired. Our numbers are reducing. Thumbs up if you are still there. Thumbs down if you are not. Okay. I'm actually happy we still have a fair number of good thumbs up. I was expecting a lot of thumbs down because, I mean, yes. So that is how we get this. So the point I'm trying to make here is sometimes you might have double loops, but you have O of n work done. That's the essential point. Yes, you are correct. That's 2n minus 1. It's 2n minus 1, but we don't care about the 2 and we don't care about the 1. Yes. So this is essentially a mathematical formula here that says, if you look at it, n plus n over 2 plus n over 4, this is essentially what we are trying to do. Because if you look at this here, we are essentially adding n by its half each time. N plus n over 2 plus n over 4 plus n over 8. And then this summation of this series is 2 of n, is still n eventually. Now, this will come up, this pattern will come up later. So I want you to understand this pattern. This n over 2, n over 4. These patterns I'm saying, understand them because they will come up later in future. And it will be easier to just use them and apply them once you know that pattern. Okay. So let's move on. Okay, so what are the ways of analyzing big O? I've come across different ways of analyzing big O. So what you can do is you go line by line and ask yourself, on this line, what is total work done on this line? Like for this line, what is total work done on this line? And then try and figure that out and add everything up, and then you get your answer. So sometimes it's more of an art than a science. So you just have to practice more. So I see people are confused about that last example I did. We can take it off to the group and we can discuss more about it the way I can explain more, because I need to continue to get through the slides. I'm sorry about that. So the key thing here is knowing important patterns are helpful. So know the patterns because the patterns are important. They come up frequently. And once you can master those patterns, you can begin to reapply them. Don't get too hung up on the constants. Ensure the highest magnitudes are captured. Don't get too hung up if you have 2n plus 5 or 2n plus 3. It doesn't matter as far as you have O of n or order of n squared. Another thing again is this. Your detailed counting analysis might not be the same with others, but the important part is to arrive at the same orders of magnitude. That is the most important part in your analysis. So we went through some patterns. These are the key patterns I noted out, and these are important patterns for you that you need to know. That's why I outlined them here. So the first one we went through was the sum of the first. So am I going too fast? Thumbs up if I am, thumbs down if I'm okay. Thumbs down if I am, thumbs up if I'm not. Okay, most people think I'm not going too fast. Okay. Okay, I'm actually going too fast. Okay, so I would try and make some magic there. So the sum of first n natural numbers is what we dealt with before. So one form of it is adding the numbers to n, 1 plus 2 plus 3 plus 5 to n. The other form is starting from n and adding it down to 1. We've seen this pattern a lot before, and we know what the complexity is, which is n squared. So once you see that kind of thing forming up, you already know that, okay, this is going to be n squared. You don't need to go through those detailed calculations again. Sum of powers of 2 up to n. That was the last example we did. It's just that we're doing it in the reverse in that case. So you could do it forward, going to n, or you could do it in the reverse. From n, adding n by its half, and that by its half, up to you get to 1. And the key thing here is this is n plus n minus 1, which is O of n. Now, as you analyze data structures, these patterns begin to come up more. Variation of 2. So this is a variation of the second of 2 essentially. Essentially, we are doing the same thing here. It's just that we're representing it in terms of power of 2 to n. and this will come up. This will come up in trees. It's essentially the same thing as the second one. But these patterns are important. I would like to highlight that you need to keep into consideration and know them. So exponential, factorial, we'll talk about that later. Let's move on from that. So now, these are theoretical considerations. If you are not, we'll share the slides. So if you are not, for purposes of interviews and real life scenarios, you don't really need this thing. But the reason why I'm including this is because you might study some of them in the textbook and you might see some of these things. So I want to clarify some misconceptions that are out there. So asymptotic analysis is what we've been doing. That's what they call it in the textbook. They say it's an asymptotic analysis. So essentially what you are doing is you're evaluating the performance of an algorithm based on its input size. Now, asymptotic notation are how we do it, which is big O. But big O is not the only one that exists. There's big omega and there's big theta. Now, there's a lot of confusion out here, right? Where people think big O means worst case, big omega means best case, big theta means average case. That is not really true. But that is what a lot of people, what you read online a lot. The reality is, when people say big O, they actually refer to mean big theta. I'll explain why as we go ahead. Because what we care about is big theta. But because it's used interchangeably with big O, you can just use big O for interviews and it's perfectly fine. It's fine. People know that, okay, in interviews, if you are doing an interview and you say it's big O, this is fine. But what you actually mean is you are talking about the big theta, if you really want to be precise. I'm saying this because when you read textbooks, you're going to encounter these things. Or if you go do deeper study on it, you encounter these things. And it can be quite confusing if you are not really familiar with it. So what is big O, essentially? Big O describes an upper bound. It means that this function is less than or equal to something. So let me give an example. Let's say when we did our accounting analysis, we got 2n plus 4. We know that this is big O of n from our analysis. But it could also be big O of n log n. It could be big O of n squared or big O of 2n. They are theoretically correct, but they're not very helpful. I will explain why with a concrete example. Now, the big omega describes the lower bound. It means this is greater than or equal to this function. So when I say the big theta of something is this, I'm saying that this function is going to be greater than or equal to this function. Now, if we get 2n plus 4 from counting analysis, we can describe it as big theta of n. We can also say it's big theta of log n. Because it's great, because that function will perform better than log n. We can also say it's big theta of 1, but it's not very helpful. Now, big theta describes the tight bound. This is where big O and big omega intersect. And that is the exact thing we are looking for. And that is what people confuse with big O in interviews. So I will explain with a concrete example. Let's say I have a number x, and I'm trying to describe it in terms of other numbers, which is essentially what we are doing. We have an algorithm we have, but we are trying to describe it in terms of other algorithms. If I say x is less than or equal to 100, right? That's a wide range. So let's say x is 10. So let's say x is 50, right? If it's true that x is less than or equal to 100, it's also true that x is less than or equal to 90. And these are all ways you can describe x in terms of big O, but it's not very helpful to us. The same thing, if you look at it the other way and say, okay, if x is greater than or equal to 10, right? We can describe it with big theta, which is true, but x is also greater than or equal to 20, x is greater than or equal to 30, 40, which is not very helpful for us. But big theta is what we're actually looking for, which tells us that x is equal to something. And from this, we can know that x is 50. Now, you don't need to know this. I'm just including this for completeness. You can skip it if it's confusing. It's just something I wanted to just clarify it out there for completeness. So let's go to the interesting parts of what we are all doing. Real life consideration. How do I do this? How do I use this in the real life? How does this help me, right? How does this help me in my day-to-day work? First and foremost, we need to do it for interviews. But after interviews, you also need to, you can use them in real life consideration for some things. Now, the thing is, big O doesn't replace the need for testing. Big O is like giving you an indication of something. It doesn't say you shouldn't still test it. Because the constants matter when you're actually testing it. What this means is that two algorithms that have the same big O order might perform differently due to constant factors. An example is some sorting algorithms like merge sort and quick sort. They have the same big O, but they perform differently. So you can look at that link if you're interested in more details. The other thing is, big O tells us which algorithm is better only if the input grows very large. It doesn't tell us which is better when the input is small. Because where this becomes important is sometimes the input is always going to be small in real life, and we know they will always be small. And the key here is that a worse big O algorithm could perform better than a better big O algorithm for small inputs. For example, insertion sort, bit merge sort on small inputs. I just put it here for completeness. You can go over it later. As you go, when we finish that of the course, it become more clear why this is. And linear search performs binary search for small input sizes. So these are just some real life considerations when you're actually like implementing algorithms. You still need to do, bottom line is you still need to do testing. And then there's some other considerations such as caching that might show up later that essentially what I'm trying to explain here is that sometimes an algorithm that has a worse big O will perform better than an algorithm that has a lower big O because of some other factors in some cases. So we can just go through it and we'll talk about this later. So for real life considerations, the key thing to note here is once we begin to get to quadratic complexity, we can't really be as efficient as we want. So typically we want to bound everything to logarithmic complexity. Sorry, log linear complexity. That is what we try to achieve when we are implementing algorithms in the real world. So algorithms greater than quadratic complexity are not scalable in practice. That is the reality, because when you start getting to the exponential, they are not really scalable. The input size, the time it takes for the algorithm to run grows too much with respect to the input. So they are not scalable again. The difference between logarithmic and linear is huge. It's a very, very big one. Logarithmic is very important to understand. And logarithmic is almost as good as constant. If you look at it in the real world, like it's really almost as good as constant. So the goal is to try and make algorithms log linear or better. But quadratic can still be fine in some cases. For anything above quadratic, it's known as an NP problem. That's the term they usually call it. But in the real world, again, sometimes the worst algorithm is chosen because it's easier to implement. And code readability also matters in the real world. So the key is to also always use discretion and strike a balance between an algorithm that is fast enough and one that is easy to implement. So I'm going to talk about time-space trade-offs here. So I mentioned earlier that we usually trade off on time and space complexity. So if you increase your time complexity, you can improve your time complexity by increasing your space complexity and vice versa. So that's what we call time-space complexity trade-off. So usually we want to optimize for time because space is usually more available than time in most cases, because of something called Moore's law. I mean, you can read up on that later, but the key thing to note here is that space is more available than time. NP means non-polynomial. It's a research term, and we don't really need to go deep into it, but it means non-polynomial. So for real-life examples, I included these real-life examples to really make us understand why it's important to pay attention to these things. So in this example, essentially what happened in the first example was this person was running a loop, right? I think I need to increase this. I mean, you can go through the link later, but this person was running a loop with n squared, and it was very slow. And they optimized it to O of n, and it ran faster. In the second example, they optimized a quadratic implementation of joins in database. They optimized quadratic to linear to make it faster. You can go over that if you're interested in I don't want to put this out here exactly. Depends on the trade-off you want to make. Correct. Yes, correct. You are very correct. Depends on the trade-off you want to make. But from my experience, we usually care more about time because space is relatively easy to get nowadays. But time is difficult to find. Time is hard. Once you lose time, you lose it. It's gone. You can't get it back. That's the problem with time. Yeah. So So I put some practice problems here for you to go through. But please, 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 make sure you understand the intuition behind the answers. Please, make sure you understand the intuition behind the answers. It's very important. It's better to understand the intuition. It's better like to understand the intuition right now. Just understand the intuition behind the answers. Because it's what helps you understand more. If you don't understand something, reach out to Slack and make sure you really get it. Then I put some things here like geeks for geeks. So like practice questions on complexity analysis. So the advantage here is that they give code in multiple languages for you to like. So if you want a specific language, you can choose your language. Focus on all problems and try and understand. They have the answers there, but again, this is not about whether you get it right or wrong. Nobody is marking anybody's score anyway. This is about you getting the intuition and self-assessing yourself that you really understand it. Nobody cares whether you get it. It's not. Nobody's going to ask whether you get it. That we are not here to do that. We are here to like make you really understand it and learn. Then, the other one is like some practice problems, but you can skip 1 and 2 because they deal more with some theoretical things and recursion, which I don't think are really necessary, unless you are really interested in that kind of thing. So I included some additional resources here that you can go through. So I tried to go through resources that kind of explain it in an easy way first. So I would highly recommend you read through this. Just read through them and try and understand them before you go read more complicated materials. Yeah. So I think, yeah, so do we have any questions at this point? I know I took your time today and sorry for overscheduling it. Next week we'll try and be a bit more efficient. And we'll work with the organizers to come and see how we can maybe make it not take a lot of people's time. So do we have any questions? Okay, so if you don't have any questions, I presume if people go through considering the worst case scenario, I was thinking multiple loops will be considered quadratic regardless. In general, they could be, but there are some situations where they are not. Now, if you are just looping through the loops, like looping through the loops continuously, like to n and to n, that's it. But when you start having multiplication and division within it, it kind of complicates things. So you have to look closely and look at it. So in general, when you have like multiplication and division within the loop, it becomes very funny. But there are patterns. Those patterns are outlined there. If you understand them, you should be good. Let me see. So we are aiming for log n next week. Actually, log n is a far-fetched one. We are actually aiming for n log n or n squared mostly. That's too much to aim for log n. It's just not realistic in the real world. A lot of things. It's a lot to assimilate right now. That's true. It's a lot to assimilate. I get it. Take your time. The videos are recorded. You watch them if you need to. Ask questions on Slack. Take your time. It's fine. What's my name on Slack? I will share my details on Slack so that you can reach you. Yeah. Okay. I think that's everything I had. Thanks everybody. I hope your brains are not too fried and have a good evening.
Yeah, thank you so much. Like this is really, really educative. I myself, I will still have to go back to watch the video again. And like we really, really appreciate. I hope everybody here is motivated. I can see some comments and I see some reactions too. This is really, really amazing. So thank you so much. I know we've spent a lot of time here. Really apologize. We didn't mean to. And we hope we work towards meeting up with the time next time. So guys, expect an email from us. Please watch out for an email, and we are going to share the resources and the recording and everything you need. We are going to share it with you. Please, if you have any other questions, please go to the Slack channel and ask those questions. It's really, really important to be on the Slack because that's the only place you can connect with our great tutors. So thank you so much, everyone. So we'll be putting today's call to an end. And if you have any other questions, maybe related to the program, you can easily tag me on the Slack too at the same time. So yeah, don't waste so much of our time. If there's any question, please go to Slack. There's no more time. Please, let's go to Slack. And so to save each other's time. So thank you everyone, and see you guys next week, same time on the same link, and have a great evening. Bye everyone. I'm going to say, yeah, to join Slack, I'm going to send an email. I've sent an email earlier. You can check your email, but I'm going to send another email on how you can join Slack and join our community platform on WhatsApp as well. So thank you so much, everyone. And, see you guys. Bye and enjoy your evening.
Guys, thank you.
Okay, bye.